Thank you. Thank you. Yeah, so my name is Chen Bainien, and I'm from Advanced Remanufacturing Technology Center under A-Star Singapore. And I'll just start. And so this talk will consist of 3 parts. First, I would like to explain the motivation behind this development effort and some of the challenges and potential use cases in the industry. Second, I would like to explain the design for each of the software components. And as you can see, we have 4 here to achieve dynamic safety. Some short simulation as well as hardware demonstration videos will be also included in this part of the talk. Lastly, our future plans. So as I'm saying, currently I'm talking about dynamic safety, and the title is real-time collision-free motion in a dynamic environment. And this is how we actually I will be cross-calling these 2 terms. So what I'm saying dynamic safety is actually to achieve a collision-free motion in a dynamic environment. So first, let's look at some familiar things. This is actually on the left side here is actually the Move It tutorial using Move It CPP. And as you can see, the robot is able to avoid the collision here. The collision, the box here is actually added before the planner started. So I took some liberty to modify the code to let the robot plan without any awareness of a block here, and then I put the block in to see whether the robot will clash with it. And to my surprise, it actually clashed with it because, well, I think we all know that currently, if you're using Move It CPP or Move Group, once the motion execution started, there aren't too many things that you can do. If there's an obstacle in the way, you cannot really do much as well. So you might say, this is more of like an effort issue. If you put in more effort to put all of the obstacles moving around in your world and make sure when you're starting the planning, everything is in there, you don't really have to face this issue. Well, my counter offer is that, well, with additional collision avoidance capability, you're able to improve safety for human-robot interactions, like Christoph has mentioned. You can also improve robustness for implementing multi-robot asynchronous operations to boost overall efficiency. For example, like multi-robot pick and place, which is one of the reasons we get to this point. The last one is also that in some complex procedural tasks that you requires, for example, like folding things where you need actually 2 hands to do this. Additional safety features will definitely be helpful here. So besides that, with these in mind, we started looking at how to implement this, and we have find out that there's no existing software architectures or legacy code in Move It to support such a complicated tasks. I think now with hybrid planning from the wonderful Picnic team, this would not be an issue anymore in the future. Besides the lack of existing software architecture support, there's also other isolated issues which I've listed here. One of them is collision checking. So collision checking can be slow sometimes. Also, like, for example, you don't really need to know the how far you're away from colliding. You just need to know whether you're colliding or not. And without the distance information, you can actually get the collision checking much faster. The second one is about replanning. For the current planning algorithm is slow and sometimes non-deterministic. Then that next one is, when do we decide to slow down and replan? And while we're actually replanning, how do we make sure that the execution is not clashing into something at this time? The last point is that there's not really a very good solution to slow down or speed up your trajectory execution in Move It. Of course, later Felix will present the scale trajectory controller, and I'm actually also taking inspiration here. So another thing is that for the trajectory replacement, it's also not very smooth if you just do it through the action interface. So with that, we come up with a new module called dynamic safety under our EMD packages that ARTC is currently developing. And within that, there's the collision checking module, which making use of multi-threaded capability to boost collision checking. And we also implemented some replanners to do replanning. Then there's also the safety zone component, which acts like the brain here. Based on how far away your collision happens, it decides what is the next course of actions or no course of action at all. The last part is a scaled follow joint trajectory controller, where we can control how fast the execution goes. We can slow it down. We can speed it up. We can also replace trajectory without causing any jerky motion. So this is your typical architecture for a MOVEit application. You have the planner, you have the trajectory execution manager, and then it sends a trajectory to your driver. And thanks to ROS control, it can abstract away some of the different implementation of robot client libraries. And we get to design different kinds of controllers rather independent of how the underlying robot client library looks like. And one of these controllers is the joint trajectory controller, which accepts the trajectory and execute them. And for our dynamic safety, we synchronize whatever the dynamic safety real-time loop is doing with the joint trajectory controller, and we put our name on it. It's now called dynamic safety joint trajectory controller. And this specific controller, because we also need to check collision, we also need to do replanning, we also need to keep our environment up to date. So we also inherit some of the parameters from MOVEit, as well as syncing with the MOVEit scene, as well as joint states, so that we get the most updated information. So for a much more detailed look, this is the scale joint trajectory controller, where it communicates with through the abstract layer with the robot client libraries. And on the left here, we're actually accepting a trajectory. And with that, we'll start doing preparation, taking parameters. We're also inheriting planner configs, and just to make the setup easier. Then after the preparation is done, all the proper data structure is created. We'll send the new trajectories to the main loop, as well as to the scale trajectory controller. In the main loop, we'll first update the environment, which includes different topic sources, such as joint states, planning scene, and Octomap. For later on, we actually have Tesseract implementation for both the Replanner and collision checker, but Tesseract implementation currently only works with joint states. It's not Tesseract's problem, it's our limited implementation. It's a work in progress. So after the environment is updated, we'll perform collision checking. And after collision checking, whether there is collision or not, we'll determine based on our safety zones to take the next course of action. If we want to slow it down, we'll be sending a scale to the scale joint trajectory controller. And this is actually through the real-time buffer provided by ROS control. I think we can also do with atomic values, but we have not just the scale as well as some of the other times to sync up here. So this actually allows us to operate at a different rate compared to the scale joint trajectory controller. So for example, if we cannot reach the 500 rates used mostly by the UR controller, we won't cause any trouble because this controller is actually still operating at 500 Hertz. And if the Hertz drop too low, this part will actually stop working, but our dynamic safety will still work at the compromise of reaction time. So if requires replanning, we'll start replanning, and after the replanning is done, we'll send the new trajectories to as the prepared action and update the environment, update our main loop, as well as update the scale trajectory controller. So the key consideration here is that compared to replanning, collision checking is actually a very fast operation, and we would like to do collision checking constantly. However, we don't want to do planning all the time because in our case, planning is actually 100 times, takes 100 times much longer than the collision checking. So this is a flow diagram to show you to showcase this much clearer. We have two separate loops going on. We have the main loop from the dynamic safety, and we have the scale trajectory controller loop. And in case we need to do replanner, we actually start asynchronously at a separate thread. And in each loop, we're actually checking whether the replanner has completed. If it succeeded and is able to meet the deadline, and then we'll update the new trajectory. Okay, so that's for the overall part. Let's look at the collision checker, how we improve its performance. So for this, we have implemented a thread pool-like architecture to have multiple runners on different threads running constantly through conditional variables. We're able to change them from idle states to active states and to other states, and also synchronize their results to get the final result. At the start, we'll actually segment our trajectories into equal length so that it's easier for both the discrete collision checking as well as the continuous collision checking algorithms to take each state and do its own work. So this part is actually not dependent on MoveIt, and we have created two kinds of contacts here. And for the contacts, it's basically all the information that's needed for collision checking. And we don't want any data racing inside, so we're actually doing deep copy for every one of them. For MoveIt, we're using planning sync and deep copying planning sync into each context. And for Tesseract, the state solver and the contact manager actually pass by deep copy by default through its get function. So it's actually pretty easy to implement it. So for the configuration here, you can see that you can configure to use MoveIt or Tesseract, and you can select the underlying collision checking library, whether it's FCL or Bullet. You can also select whether you're going to use continuous collision checking modules or discrete collision checking modules. The continuous collision checking is still work in progress. We're facing some issues with it, especially with MoveIt. We still haven't figured out why yet. Then there's the step, which previously I mentioned that we need to divide the trajectory into separate segments, and this is how long each segment is. And the segment is not based on distance, it's based on seconds. Last but not least is the thread count, how many threads we're using for the collision checking. So here's the result of our implementation. We're using FCL 0.6, which is not the default version. Comes with MoveIt 2. We're also using MoveIt 2.2.1. Here's the triangle phase count as well as what is actually inside. We have run it for 200 times, and as you can see, not only does the collision checking times decreases, it also becomes more consistent with less outliers out there. So this is a comparison for different collision checking algorithm, and we're using FCL 0.6 for both MoveIt and Tesseract, and we're using Bullet 2.88 for Tesseract. Unfortunately, for MoveIt, we're facing some issues with Bullet. There are some linking issues when it is not loaded by plugin libraries. We are not able to solve it, so it's not currently in the current data here. As you can see, with low phase count, there isn't much of a difference here. But if we have a lot of triangles here, you can see the difference. And to my dismay, I was expecting Tesseract to perform much better than this. And in theory, it should, because it returns after the first collision is detected, as well as it converts meshes to convex hull instead of just the meshes itself. And convex hull is supposed to be faster in doing collision checking. There might be something that we have done wrong here, but as you can see, it's pretty good. We still get it to around, we can still get it to 2 milliseconds on average. And yeah. So as a summary here, if we're using a much simpler setup, you can comfortably reach 500 Hertz with not much of an issue. But if you're using a rather complex setup, usually 200 Hertz of the dynamic safety frequency is also pretty comfortable. So next is the replanner. So for our replanner, once the collision is found, we actually find the start and end index pretty close to the collision, and then we'll do the replanning. However, for this replanning, what is different from what you usually do in MoveIt is that we don't do time parameterization right away, and we also remove some of the request adapters so that we don't check like whether the start and end state is valid, because we're already checking it. And after this is done, we'll combine it with these unexecuted old trajectory segments. As you can see, our current location is also updated because while we're planning, the robot is also moving. After that, we'll do a time parameterization to make sure that the path is smooth. However, there's a possibility that after smoothing it, there's going to be further collision with it. Right now, how we deal with it is that if we detect new collision, we'll just let it run to do another replanning and time parameterization again. So for the replanner configuration, it's pretty much self-explanatory. We inherited some of the features, some of the parameters from existing MoveIt nodes. One thing to note here is that for Tesseract, we also supports not only just the TrajOp algorithm, we also supports the OMPL chained with TrajOp and TrajOp IFOP, which I'll explain a bit later. So next is the safety zone, which is how what to determine what to do after a collision is detected. So here's our start time, here's our trajectory end time, and here's our current time. A look ahead time is usually manually set. And within this look ahead time is where we check for collision. Let's say if we find a collision here, then what should we do? So, so what we design here is that we have just put some of the duration here in reference. This is how long it takes to finish a loop. This is how long it takes to slow the robot down based on the current speed and maximum acceleration. Here's how long it takes to finish replanning. And as you can see, the replanning is actually stacked on top of the slowdown time, which I'll explain why. And then we just mark it down, and we created some zones here. And the first zone is, and this is our safety zone. So the first zone is the blind zone, because it means that if the collision fell into this zone, there's nothing we can do. By the time we detect it, we already collide with it. So there's nothing we can do here. For the emergency zone, it means that we don't have enough time to slow down. Then we'll just stop immediately, sacrificing to have a jerky motion there. If we're in the slowdown zone, we're actually don't have enough time to replan without slowing down. So in this case, we'll slow down and replan. If we're in the replan zone, then we have enough time to replan. So we'll just continue our path. And if the replan is successful, we'll take the new path and follow the new path along. If the replan is not successful, Let's see how it goes. So this is how it goes for the simulation. And in the case that I just mentioned, if our replan is not successful, in the case of a static obstacle, you actually will fall into the slowdown zone again. And in that case, the robot will actually automatically just slow down and replan again. And if the initial planning failed, then you will just keep replanning until we find the correct plan. So that's all for the replanning. Let's go to the scale trajectory controller. So as I mentioned, it takes inspiration from the UR, ROS, and ROS-II controller. And for this specific module, it has actually two kinds of time. One is the trajectory time, is where you add the trajectory. It's more of like a coordinate of where you are, not really where you are, not really what time it is. However, the real time is how long it takes, how long it has passed. So for example, if we're going first at at the full speed, then we go at 0.5. This 0.5 of the full speed, then we go at the full speed again. In this case, will take much longer time than the trajectory time. So what the scale joint trajectory controller does is that it will actually map it to the trajectory time. And for as your robot only only accept position commands, we only need to find the position command, for example, at this state. And how to find this state is that we find the corresponding position command. So in this case, normally it will take like this amount of time to complete this part of the trajectory. If we scale it up, it actually takes much longer here, and we're actually running at half the speed of what it originally is. So for us, we actually changed a bit more for the scale joint trajectory controller. We make sure that even the transition between different scales is gradual and based on acceleration and some heuristics that we have created. And it allows multiple slowdown and speed up operations. For example, if we end at 0.5 scale, when the next trajectory can come in, we can recover at the full speed and start again. So here is how it looks like in the simulation. As you can see, once the robot has sensed there's an obstacle, it slow down and stop. And after that, when we remove the obstacle, the robot just keep going up. And this is how it looks like in real life. Take note of the UR5 on the left here. So now it slows down to let the UR3E pass. And after the UR3 passed, it goes back to its original speed. Okay, so we have covered all of the components. Now let's look at the full configuration. So you can find the full configuration file as well as the demonstration here in this branch under EUM conference. We'll merge it into the main in a couple of weeks after this conference, but we're unable to merge it in at this time. So all you need to do is to change the follow joint trajectory controller here to the dynamic safety joint trajectory controller. And we add in the dynamic safety configurations, writing where we're inheriting the parameters, whether we allow to replan or not, which means that if we allow when there's an obstacle, we'll replan. If we doesn't allow, we'll just slow down and wait for the obstacle to disappear. We also have a small visualizer to showcase the color points that you see just now. And it is like 10 times the segments that we have for the collision checker. And this is our configuration for the Replanner. So let's see how it will go for this. And as you can see, it's a little short time. Sorry. Okay, so yeah, I'll just quickly show the next slide, and we're pretty much good to go. Yeah, so now is a much cooler demonstration where we have two robots. And I'm moving the UR5 to try to block the UR3 path to doing pick and place. And when UR3 is actually doing the planning, it actually doesn't care where the UR5 is. Yeah, so it's purely the dynamic safety is actually doing the obstacle avoidance here. Okay, I'll just keep going ahead. So as you can see previously, the trajectory is actually not very optimized, and we actually look at the tesseract and find that we have a way to deal with it. And with that, we're able to get a much smoother avoidance trajectory. Okay, I'll skip this and I'll go to the acknowledgement. Thanks everyone in the ROS-Industrial AP team for helping me, as well as the tesseract development team, the MoveIt2 team, the ROS control team, as well as the UR driver team, who I draw inspiration from. And yeah, that's all.